corrosion, degradation, and oxidation. So normally when we start talking about things in science, we like to simplify things. When you first start talking in physics about dropping an object, you do things like neglect, drag at first, right? You just keep it very, very simple. We also make an assumption that the gravity of the Earth is the same everywhere and that it doesn't really change all that much. We make a lot of assumptions. We try to make things easier. So one thing that we do a lot of times in our engineering classes is we try to just talk about perfect systems. We have this beam, we put a weight on it. How does it act? We even get into eventually, this is a beam that has this type of stress and strain. It has this Young's modulus. It has all these types of things in it. But one thing that we really need to talk about when we start getting into actually applying things is we can no longer just make things simple. We actually have to take things into account at a certain point. And this is where we're going to start talking about corrosion, degradation, and oxidation. It has to be there at some point. We are able to control some environments. Some environments are somewhat easy to control as far as humidity, oxygen, different types of electrolytes, acids, and stuff like that. Others are not. They're put in a situation and we can't control it all that well. So some simple factors we're going to look at are going to be things like water, oxygen, electrolytes, and those are going to be things that transfer electric charge. You watch Gatorade commercials and they say, hey, if you drink this, that it's going to replace electrolytes. What it's doing is it's putting ions in your body that's going to allow your body to move things properly between cells. And those are electrolytes. It also works between materials. Heat can also cause things to fall apart, degrade, corrode, oxidize at different rates, along with light. So we're going to start with metals. We're going to talk about different things that metals can do, and then we'll go through some of our other materials, and then we'll get into some specifics. So first, just really broadly, corrosion. Metals can corrode. Sometimes we use the term corrosion and oxidation interchangeably, but they are different. Corrosion is a dissolution. It's when the material is actually falling apart. We're losing material. That's when something is corroding. Oxidation, on the other hand, is when I'm actually gaining material. We gain an ionic scale or an ionic film over the top of it. And how do we know that it's ionic? Well, we're talking about metals here. And what we're going to do is we're going to bond oxygen to this metal. And going way back to the beginning, when we look at what type of material do we have, when I have a metal or something with a mid to low electronegativity and bond it with something that has a higher electronegativity, such as oxygen, we end up getting a ceramic. We end up getting an ionic material. And so that's what's happening here. We gain material. We're gaining some oxygen. It bonds with our metal. And for iron, and for iron only, we call this rust. It doesn't matter if another metal oxidizes. We don't call it rust. It doesn't even matter if that metal turns an orangish, reddish, flaky color and that it flakes apart. We don't call it rust unless it is iron. A couple things, though, about oxidation. Sometimes oxidation isn't necessarily a bad thing, and we'll get into this maybe a little bit later. For iron, rust is a bad thing. It's going to, unless we're trying to get rust as a chemical reaction out of something. But rust, it's brittle, it's flaky, it doesn't work well, it doesn't make our material better. But there are some metal oxides that are it actually improves materials. It makes materials better. Some of those would be aluminum oxide. Aluminum actually is a very, very reactive metal, and it oxidizes very, very easily, easier than iron. So how come we usually don't get upset about leaving iron outside in the wet and in the rain and in the humidity? It's because that the thin film of iron, of aluminum oxide, isn't too bad. It's very hard, and it actually can end up protecting the material. It doesn't crack, it doesn't flake like rust does. Some other ones would be things like zinc oxide, and we'll get into that a little bit later as well. So oxidation, and we're still under oxidation here. Oxidation is an electrochemical reaction. It means that electrons are being transferred. And so we just have a little bit of some reaction stuff here. I have some metal, and that metal is going to turn into a positively charged metal and some electrons. We're moving these electrons away from the metal itself. So I have some examples here. If I have iron, I can get iron 2+, and because of that, those 2 electrons are elsewhere, and so I get my electrons. Aluminum is the same thing. I get aluminum 3+, and those electrons can't just disappear, so I have 3 electrons left over. I also wanted to mention that an anode is a positively charged electrode by which electrons leave. Well, we're transferring electrons off of this. Oxidation, sometimes called an anodic reaction because of this. We are causing electrons to leave. These electrons have to do something. They can't just sit there and say, well, we love being free, unbound electrons and just sit here and do nothing. They want to become part of something else. And so here are some options. We can get those electrons to come together with some hydrogen, and we get hydrogen gas. Those electrons could end up bonding together with some oxygen, hydrogen, and we could get water. These electrons are going to do something. And one other thing that metals do is we get hydrogen embrittlement. Again, this is a type of gaining of material. What happens is hydrogen is a very, very small molecule, and it's very, very easy for it to diffuse into materials. And so when there's enough hydrogen, it's going to diffuse into our metals. It's going to sit at the interstitial sites in our metal lattice. So these are interstitial defects. And what it's going to do, it's going to reduce ductility. And what does that mean? Well, when I reduce ductility, that means I'm increasing its ability to be brittle. So it's hydrogen embrittlement. It's getting brittle because of hydrogen. So that was really quick. That was metals. I want to talk about polymers really quick. Polymers, when polymers corrode or do whatever polymers do, the wording that we normally use is we use the term degradation. It's just what we use for polymers. So polymers degrade. And what does that really mean? Well, it's this big umbrella that covers a lot of other things, such as dissolution. Again, meaning falling apart. Swelling, it can take into it some type of solvent, some type of water or something, and it can swell. Chain scission. Polymers, remember, they're these long chains, and these chains can start breaking down, so they're smaller chains. And if they're smaller chains, then they're going to have different properties. They can become brittle. So that's polymers. We can talk specifically about some things that polymers do in class. Again, polymers, it's a huge topic, and so spending any amount of time on polymers is going to take a lot of time, and we're still going to barely be scratching the surface. So we'll talk about polymers in class and answer the questions that you guys have on them. Ceramics. Many ceramics are immune to corrosion, or at least a lot of forms of corrosion. The reason for this is ionic bonds are very, very strong, but also they're already oxidized. If we look at it, what is our oxidation in our metals is an ionic scale. Well, that's exactly what a ceramic is, except for it's not a scale, it's the whole entire material. But we have some metal, something that has some mid to low electronegativity, and it's bonded to something that has a high electronegativity. So it already is kind of in the form of oxidation. Some people consider ceramics already corroded. But when they do fall apart, since they can't oxidize, they have dissolution. They fall apart. Again, we can talk about maybe some specific ceramic stuff in class. What I want to get into is I want to get back to the metals. That's what everybody likes to talk about. So I want to talk about some common types of corrosion in metals, particularly metals at least. One of them is galvanic corrosion. It's an electrochemical process where one material corrodes in preference to another. So I have two materials here. We have this screw, and it is screwed into some other metal. Where those two things come in contact, I have two separate metals. When there's some type of electrolyte, something that allows for electric charge to pass through, some type of ions to move, we're going to get galvanic corrosion. Maybe you did this in a chemistry class where you maybe made a battery by putting two pieces of metal into some acid, or you maybe electroplated something by putting one type of metal in one side, put another type of material of metal on the other side of some in some solution. You passed a current through there, you applied a voltage, and some of one material came off and plated the other side. That's exactly what galvanic corrosion is. So some examples of this would be when we coat iron with zinc. Maybe you've heard of galvanized sheet metal, or you've gone to Home Depot or Lowe's or something, and you went to go buy some nails or screws, and it says that these are galvanized. What it is they've galvanized it. They've made it to where one material is going to corrode in preference to the other. And if you coat this entire piece of metal with something that's going to corrode, then the electrolytes can't get into the other material. So I guess what we're looking at here is if we have let's say a nail, and this is made out of iron. It goes outside, we put it in a fence, we do whatever with it. It's going to eventually corrode because it's in contact with moisture, humidity, oxygen, and all those things. But if I dip it in zinc, and so I coat it, maybe I shouldn't be using red here because red will look like it's rusting. But this red here is going to be my zinc coating. And I coat it all the way around. What's going to happen is zinc is very reactive. It's actually going to react and it's going to oxidize very, very quickly. But it's going to create a zinc oxide. And this zinc oxide is a very, very hard and a very, very, it encapsulates this nail. Which means if it's completely encapsulated with this really, really hard zinc oxide, how am I going to get an electrolyte? How am I going to get moisture inside so that I can start rusting this nail? You can't. We've basically encapsulated it with something so that it's protected. Another thing that, another form of galvanic corrosion where we could actually make this work for us is in a water heater. Water heaters, we bring water into it, we heat it up, so there's some heat there which will accelerate corrosion. And our water is going to have minerals in it, and those are electrolytes. It's going to cause corrosion to happen. And so what there is there's an anode in it. Basically, it's just a piece of metal that you put in there. It's a big stick of metal that you put in your water heater. And if you've ever opened up a water heater or had to get it removed, you'll open it up, and this thing, it's been completely eaten away. It's got holes in it. It's corroding. That means it did its job. What's happening is that zinc anode, again, something that corrodes somewhat easily. When there are those chemicals, those electrolytes in the water that are going to want to corrode something, they're going to go to the thing and they're going to corrode the thing that can corrode it the fastest. And they're going to go corrode that sacrificial zinc rod rather than the actual water heater itself, which will prolong the life of your water heater. We have crevice corrosion. It's a localized attack at a gap or a crevice between two metals. I have this picture here. Two metals were riveted together. It looks like they were painted somewhat as well, which can help with corrosion, but maybe they missed a spot when they were painting it or something happened. But somehow our fluid our electrolytes got into this seam, into this gap. And what happens is they get in there and they just sit in there, and it gives them plenty of time to begin the corrosion process. It's not just the fact that it runs across it as a bead of water is dripping down the surface. They get inside this crack, they get inside this gap, this crevice, and they just sit there, and it will work on it and work on it. So examples, there's an example here, but some other examples are if I have some bolts, maybe some washers between the bolts and the surface. There are little gaps where things can get stuck in there, and it just works on it and works on it until it begins corroding. We have pitting. Pitting is localized, where we have localized holes or cavities are formed in the material. Sometimes you can see these pock marks on materials. Pitting is a difficult one to know how bad it is. And the reason for this is I have this surface and I have something that's corrosive on it, some type of chemical or something that wants to start eating away at this, this spot here. What's going to end up happening is it's going to go ahead and start corroding it. Okay, we see this pockmark. The problem is we don't know what's going to happen next. And so there are a few things that could happen, and this is why pitting is very, very scary. One thing that can happen is this pockmark can widen out. It just gets nice and wide. That's one thing. It's not great, but it's actually the best of all the things that could happen. Because something else that could happen is it just gets deeper and deeper and deeper. I get this really long, this really deep pit. That's not good. More material loss, especially if there's going to be maybe some bending or some twisting or something that happens. I've lost stability here because I'm no longer having this material bound together. That's not good, but there's even worse things that can happen. Sometimes I have this little hole, but what it's going to do is it's going to create a big gap underneath. And it's very difficult to figure out how big do we know this gap is if I can only see the opening. How do I know whether it's big or little? And once this happens, things can accelerate relatively quickly. I have a lot of surface area around here, which means that electrolytes and water can get trapped inside this pit, and it can just keep working and working and working on it, and it will corrode it faster and faster and faster. We have intergranular corrosion. These are corrosion attacks at the grain boundaries instead of the grain. So normally what happens is, and if we go way back to when we were talking about defects in materials, one of those defects, our two-dimensional defect, was our surfaces. Surfaces are considered defects because it's a break in our crystal lattice. And so if I have a material, this lattice goes forever deep, forever to the left, forever to the right, forever in front, forever in back, but there is nothing on the top of this. So that means all of these atoms are bonded together in all directions. The ones in the center, they have atoms surrounding them all over the place, but the ones on the surface don't. They're open to the top. They have some want. They're high energy because they're missing something. They're not completely surrounded. And so when something like oxygen comes up, it's going to be somewhat reactive, and it's going to be able to bond onto these spots that are, waiting for something else. It's higher energy. It's looking to bond onto something. So that's how corrosion normally works. Intergranular corrosion, it's the same idea, but instead of just dealing with the surfaces, we're going to be looking at the grain boundaries. The grain boundaries are also a two-dimensional defect. It is an interface between two grains, and sometimes our corrosion is going to be attacked at that high-energy grain boundary. This happens in stainless steel. Stainless steel has its iron with carbon, chromium, and some other stuff normally in there. But what's going to happen is as time happens, maybe when things heat up, whatever causes it to happen, the chromium and some carbon are going to precipitate out of these grains. These grains no longer have the same percentage of carbon and chromium in them anymore. And so on the one hand, you can say that's not good because, well, I wanted my material to have this exact amount percentages, and again, thinking about phase diagrams, how things change as we change the amount of, let's say, chromium is in iron. We no longer know necessarily what percentage of stuff we have in here, but what's worse is it precipitates to the grain boundaries. And so in these grain boundaries, we actually get these chromium carbides that just sit there, and those don't bond as well as these grains bond to each other. It weakens these grain boundaries and can cause failure. We can get selective leaching. We get a component within an alloy that leaches out. So here is an example, zinc leaching out of brass. Brass is a mixture of zinc and copper. And one of them, under certain circumstances, the zinc will want to leave, the copper's fine staying, but the zinc wants to get out of there somehow. And so what it does is it diffuses out and it comes out and it gets pulled out of my material. Again, what happens is I don't have the same material I used to have because I am losing zinc. So my percentage of brass is going up and my percentage of zinc is going down. I don't have the same material anymore, and I get this corrosive stuff coming out of my material. We have erosion corrosion, degradation of a material due to a mechanical action. There's a picture here. I looked up some pictures online. They all looked somewhat similar, and so it wasn't helping kind of get a picture of what's happening. So I found this little cartoon instead. If I put two pipes together and there's going to be this solder drip, this little solder point here, I have water flow. This little drip here, this little inconsistency in where my pipes join together is going to cause some turbulence. This turbulence is going to speed up this water and it's going to erode away part of my pipe at a faster rate because of that speed, especially if there's something inside of this water. Maybe there's some abrasive material. Maybe there's little pieces of metal, or there's little ceramic ionic particles, or maybe there's some sand or something in here. The more abrasive is, the worse it's going to be, but it's corrosion due to some mechanical action. There's stress corrosion. This is corrosion that occurs at a crack in a corrosive environment. So we talked about, fatigue, and we talked about creep, and we talked about how this is a bad thing, and we get these cracks, and these cracks will slowly propagate. Well, what happens if we get this crack, but we're also in a corrosive environment, and so inside this crack, we're actually getting corrosion as well? It's going to accelerate our fatigue and our other problems that happen. So that's not good. It's not good to get these little cracks, because once we have these little cracks, yes, the cracks can grow on their own through loading and unloading or through constant loading, but we have to keep in mind that things are more complicated than just loading and unloading. We're in this environment that's corrosive, and it can also add to this crack getting worse and worse and worse through corrosion. So we talked about a whole bunch of different ways that things can corrode. So the question is here, how do we fix this? There are a few ways. This is by no means all the ways, just a few quick ones. One is we can insulate. We can put some type of physical barrier in there. We can make a barrier from the environment. That's what we can coat something. We can paint something. We can put a ceramic coating around something. We can put a physical barrier. We can insulate it from other materials. If I have two different types of materials in an engine that are going to be in contact together, and this engine has there's fluids flowing through it, and there's air, and there's high temperatures, it's an area that could corrode really, really quickly. But I have these two metals that are in contact. What do? Well, we could put a gasket between them. We could put something between them that is, even if it's just a thin piece of paper or something, we can put something in there that so those two metals are not in direct contact with each other. And what that's going to do is it can help insulate so that we don't have direct contact. It means that maybe we won't get that galvanic corrosion as easily. We could reduce cracking and we can reduce stresses. That can help fix some corrosion problems. Some ways to do this is we use better materials. We don't use as cheap materials that maybe are weaker in the first place. Those cracks won't start as soon. Another way is we could get a better design. We could add something into our design to strengthen our material so that it's not bending as much and so those cracks don't happen as easily. We can add inhibitors. Inhibitors are adding a chemical to an environment, to an electrolyte, to a solution, to a fluid, to whatever. And what it's going to do is it's going to help slow that corrosion rate. We could also just use corrosion as a benefit, such as when we galvanize things. So there are a lot of real-world examples to these. Recently, a bridge nearby the college, there have been some problems, and they found that, it was corroding quite a bit. And so they took them, it wasn't a big bridge, maybe just 50 to 100 feet, but it took them a year and a half. They had to strip off all the paint. They had to take off all the rust. They had to fix all the corroded parts. They had to repaint it. It caused traffic problems, all kinds of things. There are lots of real-world examples of corrosion. I have 3 things here, and I have already opened them up. I'm going to try to remember to add these to the description in the video so that you can click on them as well. One of them is bridges in general, the Golden Gate Bridge. The question is, how often do they paint it? Why do they paint it? And all those things. So this is about the bridge, and they talk about some misconceptions about how often it's painted. Goes through the history of what types of paint they use. They use lead-based paint back a while ago. They started cleaning that off. They changed that top coat to a different type, from a vinyl to an acrylic emulsion. And they talk about, there have been some major painting projects that they've had to do, but mostly they try to just do touch-ups. Instead of repainting the entire bridge, they just try to touch it up, and that painting is going to help it stay away from the environment so much. It's over the water, near the ocean. It's going to be in a corrosive environment. So the better they can protect the bridge itself from that environment, the better. And so painting is one way to do that. Something else that happened a while back was there was that water, drinking water issue in Michigan. I don't remember all of the details of it, but they were using one source of water for a while, and it had certain chemical properties. It was scaling up the pipes with some things that weren't good. It was creating a scale inside a pipe. You've probably seen pictures before of opening pipes up and seeing this nasty scale on it. It's kind of gross thinking that is where our drinking water comes from. But at some point, they switched the source of the water. They switched to a different source, and that other source, as it ran through the pipes, it had different chemical properties, and it actually caused some of that scaling to start coming off, and it came off relatively quickly. That's why the water changed so drastically so quickly. And so the idea was, why don't we take and we can change out the bad pipes, put different pipes in, problem solved. And that is true to a point, but we have to think a little bit more long term here. And this is the paragraph that I really like right here. So this person they were talking to, this researcher, warns that the use of the copper replacement tubing may actually accelerate the corrosion of the remaining lead sections of the pipe due to galvanic corrosion. I like this because it's thinking about the problem a little bit bigger. Sometimes we say, oh, it's a simple problem. Just remove that pipe that's bad. We put a new pipe in. But remember, if we put a new pipe in, a copper pipe, what about all those other pipes that it's in contact with? You're going to get galvanic corrosion. That can cause even more problems possibly in the future. So these are real-world examples. Then I have this This Old House video. They took some copper pipes. They were redoing a house. This is a brand new copper pipe. They cut it open and it looks like it's nice copper and everything. That's because it's brand new. There's this pipe in the middle they cut in half and it's green on the inside. It's been oxidized, but you know, it looks pretty good still. It's just been used. The pipe all the way to the left here, it's been oxidized, but we also see these dark green spots. Those dark green spots are pits. This is probably some type of horizontal pipe, and when the water turned off, the water just sat there and it worked away, and eventually you're going to get things like holes. It's going to pit so deep that you get a hole through your pipe, and then the water drips. And so this is a 6-minute video. They kind of talk about the different pipes. They talk about the whole aspect of it. So there's some pits that went all the way through on some images. Some interesting things. It's all the way around us and everything because, well, we live in an environment that is going to have corrosive material. So we can't just apply it sometimes. It has to be applied all the time. Now, this last part here, it doesn't necessarily fit in with corrosion, but I figured it would be an interesting spot to put it in because it is a reactive thing. Corrosion is a reactive process. And we need to understand that as a material has more surface area, it's more susceptible to reactions. And this also is something that's important with corrosion. But what I want to do is I just want to kind of put a little plug in there for branch material science nanotechnology, looking at things that are very, very small, very, very small things. And that is one benefit of nanotechnology. It's not the only benefit, but one benefit of it is the fact that these things are very, very reactive. Using nanoscaled materials, nanoparticles, maybe for medicine or something like that, because they're reactive, could be a very, very good use. And so there is a quick way just to kind of visualize how surface area can increase reactions. If you get 2 cups of water and 2 Alka-Seltzer tablets, those tablets that you open up, you throw them in the cup and they dissolve. The bubbles come out of them. You watch them in those movies when people are really stressed out. But if I get 2 cups of water, 2 Alka-Seltzer tablets, and one of the tablets I keep whole, but the other one I grind up into a powder, if I drop them both into the water, the one that stays whole, it will dissolve. It'll take some time, 30 seconds, a minute, something like that. You'll see the bubbles coming off. The one that is a powder, when I drop it in, it's going to react much, much more intense. It's going to bubble up all at once because there's so much more surface area for it to react. It's going to react all at once. It doesn't have to eat its way through the material necessarily to have that happen. Another way to think about this is if I have this tablet, there's some surface area on the outside, and if I cut it, it has the same surface area as it did on the outside, but plus it now has those 2 cuts. And if I cut it again, it has the same surface area as the outside, plus the original 2 cuts, plus the next cuts I made. And as I keep breaking it down, I keep adding more and more surfaces, a lot more surfaces for it to react. It can react very, very quickly. It might even make your glass of water overflow depending on how full it was, because all those bubbles will push the liquid up out of the water. And anybody who has ever had to start a campfire or maybe a wood stove fire or something like that, you know that you're going to also need fine material to start the fire as well. You get wood, but you can't just get a log and hold a match up to it. You need to get something that has surface area. You get little sticks so that there's surface area all the way around it that can burn. You get dry grass, something that's really flaky and wavy, and maybe you can crumple it up a little bit. One other thing you do is you can get magnesium. You shave off magnesium and it will burn relatively quickly. But again, it's all due to the surface area. And we know that because magnesium as a solid, a large solid, I should say, isn't going to burn. I could take a big, pound brick of magnesium and I could throw it in a fire and it's not going to blow up and it's not going to start on fire. That's because there's just so little surface area for that magnesium to burn with.